Okay, so we're going to talk now about the X-ray equipment, which is chapter 5 in your Carlton book. I did take some slides from Bouchon along with another physics book, so if there's some stuff that you don't recognize, it's because I've got it from other places. All right, you have objectives here. Make sure that you're able to answer the objectives clearly. Quite a few of them. All right, so basic stuff. We're going to start very basic and we're going to work our way up into more complex. So the two types of X-ray equipment, there's therapeutic and diagnostic, and diagnostic obviously is what we're focusing on. So we have a 10 to 1200 MA, and we have 0.001 to 10 seconds and 25 to 150 kVp ranges. So tables. We've talked about this in the past, so they're uniform and their radiolucent surface is carbon graphite fiber, and it's reduced absorption of photons. So that's why we use the carbon graphite. It has to be easy to clean, free of crevices that could collect contrast, and difficult to scratch. They also have to have a Bucky tray, or if you guys are completely digital, a digital receptor underneath. Okay, so there's fixed and tilting models. So the tables can go anywhere from 90 to 15 degrees. And actually, one book I saw it was 90 to 30. So either answer. So 90 degrees in one direction, which means it stands all the way up, and 15 to 30 degrees in the opposite direction, so the head down. There's a footboard that clips on, and we do that for the patients to stand on, and there's shoulder supports when we're putting the head down with hand grips so that the patient can hang on, especially during a myelogram. There's also compression bands that can clip onto the table. We can use them to restrain patients. You have to make sure that they can release, otherwise it's false imprisonment, so you have to be careful of that. And we can use them to compress abdominal tissues so it's more uniform, and to compress the ureters in an IVP. So table supports, there's a lot of different configurations on how the tube is suspended. So there's the overhead, which is the ceiling suspension. That's what we have. It allows for longitudinal, transverse, and vertical, and it detents and locks to the table and the wall bucky. There's floor to ceiling, so it has a pair of rails, the ceiling and one on the floor, and it allows for longitudinal movement, so it only goes in one plane. And there's the floor. It's a tube support column mounted to the floor. The thing about those, it has to be counterbalanced or else it'll tip over, so you have to be careful. So there's mobile units. Most are mounted to the floor, so that's kind of like what you see in the IR. There's C-arm, there's mobile C-shape arm to support the table, image receptor, same thing. Tube and image receptor are fixed in opposite ends of the C-arm and can be ceiling mounted or floor mounted for mobile or surgery. There's upright units, so there's the chest unit that we use that we can, we call it an upright board, so we can do chest and abdomens, AC joints, cervical spines. We can do anything on the upright board. I've even done pelvises and hips and knees and everything. So other specialized diagnostic equipment, there's mammography, which has dedicated units, tomography, which is an adaptation to your regular overhead tube. You have dental and panoramic units, which are specialized and they rotate around the head. There's computed tomography, there's radiation therapy simulators, and there's urology. So power for X-ray generators. So the incoming line current, the single phase power and three-phase power. We're going to talk about that a little bit, and this is coming in, so incoming line current. So 60 hertz of alternating current, so AC, right? The root mean square, so the RMS voltage is between 200 to 240. So nearly all X-ray equipments are 210 to 220. So it's 110 typically coming in. We have 2, we double it, so we have 220. All right, power is called incoming line current, and mains and is supplied at three-phase power cycles. So we're going to talk about that. One half of the wire is called above ground, the other half is called below ground potential, with each carrying 110 to 120 volts. So the US is 60 hertz of alternating current. So two hot wires reverse polarity 120 times per second. The two lines are not in phase with each other, resulting in 210 volts. So with single phase power, so potential difference drops to zero with every change in the direction of the current. So 70.7% of peak voltage, so we're losing a lot there. With full wave, the X-ray tube is experiencing no potential difference. So the X-rays, photons are 120 times each second on a 60 hertz line. So here's single phase, so the incoming power you can see here, and it drops to zero, and then we have it here and drops to zero. That's why we have that 70.7%. And then here, this 60 hertz line, an exposure of 0.1 second with the single phase full rectified unit. So that's where you see those diodes where we're rectifying it. So here you can see we dropped to zero, but there is no lag here. So we dropped to zero with each cycle, but no lag. So we call this pulsed here. So this is 6 pulse and there's 12 pulse. Multi-phase power or three-phase power, so it's produced by the generator and it's how it's supplied from the power company. So each peak wave begins to drop to zero. The overall potential difference is boosted back to peak by the next phase wave. So this way, with the multi-phase, it never drops to zero. So full wave rectification, the net voltage produces a voltage ripple. So we see a ripple going across. So this is with the multi-phase. So you can see here how we have a wave here, then we have a second wave here, we have a third wave here. So they're just, it's out of phase. There's multiple phases running at the same time. So when you see that, we have what's called voltage ripple. So you can see we just have a ripple. We never get back down to zero. You can see here we have a very small ripple compared to this ripple. So when we're looking here, we have single phase. So we have 100%. And then we go here, we have a 50%, so, and then we have 10% ripple, and this is three phase 6 pulse, this is 3 phase 12 pulse, and this is high frequency, so we're at a 1% ripple, which is great. So that's radiation, relative radiation output. This is tube kVp, so you can see here we're at 100% ripple, and we're at a 3 phase 6 pulse, we're at a 13 to 25% ripple. And with our 3 phase 12 pulse, we're at a 4 through 10% ripple, and high frequency, we're at a 3 to 4% ripple. And then here with our tube average MA, if we're at a 1 phase 2 pulse, you can see here, we're at a 3 phase 6 pulse here, and we have a 3 phase 12 pulse with the high frequency. So as you can see, our goal is to hit the high frequency. When I started in X-ray, I was working on a 3 phase 6 pulse, so it changed our technique quite a bit. We had to adjust as we went to the high frequency generators. So let's talk about the basic X-ray unit. So there's the main X-ray circuit, which has the exposure switch and the timer circuit, and then we have the filament circuit. Really important that you guys watch the ASRT video. It's under the student sources, and it's under physics, and you'll see it there, the circuitry, and it breaks down the circuit really nice for you and explains what each component is. They've done a really nice job. One thing to remember, and I know Jerry talked about this, is that the radiographer is located on the low voltage side of the circuit. So if we do get electrocuted, we're electrocuted with only 210 volts instead of 210,000 volts. So with the step-up transformer on the high voltage side, there's a big difference. So we're always on the low voltage side in case we get shocked. Let's hope we don't, but just in case. Okay, so there's the primary circuit and the secondary circuit. So you can see the color differences here. Here's your primary circuit, here's your secondary circuit, and here's your filament circuit. So there's 3 main areas here. So primary, secondary, and filament. We're going to kind of talk about what each component does. All right, so the primary circuit is your low voltage side. It consists of the main power switch, circuit breakers, the auto transformer, the timer circuit, and the primary side of the step-up transformer. So the secondary circuit, which is the high voltage side, consists of the secondary side of the step-up transformer, the MA meter, the rectifier bank, and the X-ray tube, except for the filaments. Then there's the filament circuit that consists of the rheostat, the step-down transformer, and the filaments. And I'm going to talk about why it's a step-down transformer on the filament side. So here is the circuitry. So we have the incoming power here, and we have a circuit breaker, and you've got your auto transformer. And we've got our primary circuit here with our KVP meter, and you have your step-up transformer going to your secondary circuit. So we want high voltage on this side because this is the anode side. So we want to be able to pull those photons across. So, or electrons, I should say, not photons yet, they're electrons, right? So on the filament side, we're going to take the filament circuit here and we are going to step it down. So we want low voltage here on this side so that we have a big potential difference between the filament and the anode so that you are going to pull those across due to the voltage difference. All right, so we have the step-up transformer and we have rectification to make sure that we have direct current. You've got to have direct current going to your X-ray tube. And here on your filament side of your circuit, we have some rheostats here, and you can see it's a step-down transformer, and it goes to, there's two lines coming off, and the two lines are for your small filament and your large filament. All right, so the main circuit, so the primary circuit, when we talk about it, supplies the X-ray tube with properly modified power, so that's what produces our X-rays. Modifies the incoming power to produce X-rays by a sequence of devices. It boosts the voltage to a range necessary to produce X-rays and permit the radiographer to adjust the amperage, the voltage, and the length of the exposure. So the main circuit has the main switch and circuit breakers that are usually enclosed in an electrical box. So the exposure switch is a simple connection that permits the current to flow through the circuit, and the timer circuit is intended to end the exposure at an accurately measured preset time. So the exposure switch activates the rotating anode. The anode must be turning at a sufficient speed to avoid melting of the target. There is a circuitry that prevents the exposure until the anode is turning at the correct speed. So it's a two-step switch. So you know how you rotor up and then you expose, right? It won't let you expose until it's done getting the anode to full speed. The exposure switch must be attached to the control console to prevent operator exposure. So when we come into your facilities and we see that the exposure switch isn't mounted to your control panel, we will zip tie it so that it is, and it's actually a Title 17 law that you have to have it attached. Equipment must be designed to prohibit the X-ray tube from being manipulated into a position where it could expose the user. So you can't have the X-ray tube pointing at you when you make the exposure. And a potable cord is 6 feet long to allow the user to be far from the source. So all switches must be dead man, meaning the exposure may only occur while depressed. So if you drop dead while you're making the exposure, it terminates the exposure, which is great, right? So hopefully you don't drop dead. All right, the timer circuit. So electronic timers are capable of accuracy as short as 0.001 seconds with a 1 millisecond delay. So milliamperes per second timers use a falling load generators and sometimes capacitor discharge units, and we'll talk about those a little bit later. They monitor MA and time on the secondary side of the high voltage step-up transformer. When desired MAS level is reached, interruption of the circuit and the exposure is stopped. So the automatic exposure control timers, so AECs, that's what you guys use all the time. There is an auto transformer, is controlled by KVP selectors on the control console. It modifies the incoming line voltage. There's minor adjustments, so you can go up by 10, or major adjustments, and where you can jump by 10 kVp at a time, and minor from 1 to 2 kVp at a time. So the primary circuit, the main power switch, so it's an on-off switch for the unit connected to the facility's power supply. There's a line compensator, a device usually wired to the auto transformer that automatically adjusts the power supplied to the X-ray machines to 220 volts. And there's circuit breakers. They protect against short circuits and electric shock, thank goodness. And auto transformers, an adjustable transformer controls the KVP selector when operating the console. So important stuff. Your primary circuit, so there's a step-up transformer. It's used to increase the voltage of the auto transformer to the voltage necessary for X-ray production. So the timer circuit, so it's the exposure timer, located in this section because it's easy to control. So turn on and off, a low voltage, then a very high one. So the timer circuit variations include the synchronous timer and the electronic timer. All right, so your AEC device serves as the same role as the timer. The patient's body part of interest is variable in determining when to terminate the exposure. So uses a device called an ion chamber to measure the amount of radiation and will terminate the exposure. And we're going to talk about what the backup timing and stuff needs to be when you set the AEC. So at the console, the radiographer has selected the exposure factor, so your KVP and your MAS, along with other parameters, and presses the exposure button. In the primary circuit, a voltage is determined by the auto transformer and applied to the primary side of the step-up transformer. A voltage is selected from the auto transformer and applied to the filament circuit. With the voltage and the current selected, the stage is set for the rest of the circuit. So here, looking at the, this is your primary side all over here. So this is your low voltage, this is your high voltage side. So here's your auto transformer, and this is your voltage meter, making sure that you have the right voltage. All right, so your secondary circuit, which is this side over here, begins with the rest of the step-up transformer. So it is the step-up side. It's not the primary side, but the secondary side. So it has an MA meter, so a device placed in the secondary circuit that monitors the X-ray tube current. And you can see here there's rectifiers, which we need within that secondary circuit that convert the alternating current to direct current, which is really important. We talked about the PNNs, NNPs, and the diodes that we use and why in our last lecture. Okay, so when we talk about the secondary circuit, we're taking the single phase, full wave power, so 100% ripple, right? Here we have 100%. We take alternating currents, so 3 waves can be phased or synchronized, so we can take multiple. And 3-wave rectification, so a 13 to a 3.5 ripple, so you can see from a 13 to a 3.5, you just see a little ripple there, which is great. So this is alternating, and now we're at 3-phase full rectification. That's in this portion here. So we've got our rectifiers here. All right. So high frequency, so that's full wave rectification with the 1% ripple. So rectifiers, they're one-way valves and are necessary to route electricity through the X-ray tube correctly. So here with our filament circuit now, so we've covered the primary circuit, the secondary circuit, now we're going into the filament circuit. So modifies incoming line power to produce thermionic emissions. That's the goal. So incoming line needs to be modified to about 3 to 5 amperes and 6 to 12 volts. So supply is directly drawn, from the main circuit supply, represented by MA, and controlled by the operator. So we usually have ranges from 50, and then it goes 100, 200, 300, etc., up to 500. It can go up to 1200 depending on your units. Many units have a meter for accurate reading of amperage, so the current is then sent to a step-down transformer and modifies it to the appropriate amperage to reach the filament. There's a slight shift in the quantity of electrons in the thermionic cloud around the filament, so we put in current stabilization devices such as frequency compensators or voltage stabilizers or space charge compensators. So when we look here, we have our filament circuit coming through, and we have our step-down transformer. So we have rheostats here, and then we have a step-down transformer, which takes the high voltage to low voltage. Now, why do we want to do that? voltage and amperage are inversely related. So we want to get the most amperage we can out of our filament circuit. So we're going to take the voltage and we're going to drop it down so we can bring the amperage up, which is how many electrons we're going to be able to boil off through thermionic emissions. So that's the reason why we have the high voltage on this side and we have the low voltage on this side. So you have the step-up transformer here on the high voltage side, and we have a step-down transformer here because we want low voltage because we want high amperage because they're inversely related. Okay, so on the filament circuit side, we have the rheostat, and what is that? It's a variable resistor controlled by the MA selector on the operating console. There's an exposure timer, so it works in concert with the rheostat. Together, they determine the quantity of electrons boiled off the filament and available for X-ray production. There's a step-down transformer. It's used in the filament circuit to increase the current by reducing the voltage that is applied to the filament. So here is the whole thing all together. So 1 is your main breaker, 2 is your exposure switch, 3 is your auto transformer, 4 is your timer circuit, 5 is your auto transformer. It's a step-up transformer. Oh, it's your high voltage step-up transformer. Yep. And 5, so 6 is your 4 diode. There's 4 of them. Rectification circuit. 7 down here is your filament circuit variable resistance. And 8 is your filament step-down transformer. 9 is your X-ray tube. And 10 is your rotor stator right here. That's the electromagnetic induction spinning your anode. Okay, generators. So let's talk about those. There's single, multi-phase, high-frequency, capacitor, discharge mobile units, battery-operated mobile units, and falling load. So single-phase generators, it's full-wave rectified. We have 2 pulses per hertz. There's 120 pulses per second, so the voltage ripple is 100%. The voltage in the tubes drops to 0 twice per period or cycle. So with multi-phase, 3-phase generators, so full wave rectifier, we have 6 pulses per hertz, 360 pulses per second, 6 unusable pulses per cycle, known as the 3-phase 6-pulse waveform. So the voltage ripple is 13 to 25%, and the voltage never falls below 75 to 87% of the peak kilovoltage. So 35% more average photon energy than full wave rectified single phase. So multi-phase, 3-phase generators. So full wave rectified 12 diodes. So 12 pulses per hertz, 720 pulses per second, and voltage ripple is 4 to 10%. And in your Carlton book, they don't talk about this 12 diode, so just be aware. Your power rating, so the greatest load generator can apply to the tube. So you calculate the formula by voltage times amperage equals watts. So the X-ray generator power rating expressed in kilowatts. So high frequency generators, you take AC to DC power, converts and inverts. So full wave rectified units can produce 12 to 13 kilohertz waveforms. So voltage ripple is 3 to 4%, which is really good. So if we look back at this, you can see here, if we're looking at the tube KVP, we're at 3 to 4% ripple with a high frequency, which is great. And then our amperage here, and we've got our output, so it's 1%. That's great. Okay, capacitor discharge mobile units. So rectification circuit charges the capacitor instead of the X-ray tube. The signal indicates when it's ready and has a charge and charge to the appropriate levels. So you depress the exposure switch and it triggers a discharge of the X-ray tube. So the disadvantage is that it may continue to discharge after the usable exposure. So that's not good. Exposure begins at the peak voltage and then decreases. It's called wave tail cutoff. And it provides an RMS voltage significantly lower than the peak voltage. So you can see here we ramp it up kVp, and this is our charging period. So once it hits the charge, a signal comes on, you can start the exposure and then it drops here, but it's still inconsistent. So You have to be careful with these units. All right, battery operated mobile units. That's usually what you're operating with. They're what we use now. So they supply non-pulsating direct current due to the battery. It's similar to a three-phase 12-pulse unit. Obvious advantage as provides current similar to the three-phase 12-pulse or greater frequency. So that's a huge advantage. Falling load generators, so they start with really high amperage and allow it to fall during the exposure. So maximum use of the tube limits, so it takes the max tube limit and then drops down the exposures from there. So it shortens the exposure times, which is great, and it utilizes the tube's loading potential to a much greater extent. And it begins with the highest MA. So here's an example of a falling load. So here we're starting up here at about 650 MA, and you can see it drops down at 0.1, and then it drops down again at 0.3 to 500, drops down to 400. So it just keeps falling until the exposure is complete. So here's your AECs. So they're also called phototimers. All of us oldie moldies, we call them phototimers. They're ionization chambers. There's usually 3 of them, and they're real thin. They're about 5 millimeters thick, and there's a minimum reaction time with them, and you need to set up a backup time with them in addition. So here's where they're located. So you have your X-ray tube, your patient, and here's your ion chamber right there, and then your receptor. So you also have a circuit from here, so it communicates to terminate the exposure. All right, so the minimum amount of time required to terminate the exposure in AAC is 0.001 seconds. So it's not recommended for small body parts, as it takes that long for it to recognize and then shut off. So if you're doing a finger, it's going to be overexposed, so you have to be careful. The backup time, so the equipment often allows the tech to set a backup time, and actually all the equipment does, should be set at 150% of the anticipated manual technique. So if, you know, a hand is whatever technique, you're going to set 150% of what you normally shoot a hand or KUB at. So you look at a person, it's, you know, I don't know, let's just say, you know, they're 20 mass, and you're going to take that and you're going to take 150% of that and set it as a backup so it'll shut off. Because if you don't have safety mechanisms in place with your equipment where you can expose, if you're angled at the chessboard or you're angled at the table and you have the chessboard backup timers or photocells on, you are going to be radiating until it shuts off. It hits the max backup. So you should do 150% of what you think the person should have. So the maximum exposure, according to US law, is 600 MAS. So if you don't know the patient's really big, what you have to do is set your backup time to 600 MAS. You're not allowed to go above that. So that is a test question. That's probably on your national exam, both of these. So when you're setting your backup time, it should be 150% of the anticipated manual technique or maximum 600 MAS. So you'll have to know that. All right, so that is your X-ray equipment in brief. Make sure you read Carlton. Bouchon isn't too bad in this chapter. He has a lot of stuff about rectification and transformers and all that good stuff. So make sure you study up. Jerry will be doing classes for you in addition. I will post a quiz that kind of encompasses all 3 chapters.